Let me begin.
I'm going to be so bad. I don't know how to use it.
All right, guys, let me get started. I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day. Again, I thank you for this class, for the students. Just ask you to bless our work today, Lord. In your name I pray, Lord Jesus. Amen. All right, so I've got a few examples for you guys today, unless you guys got a question. What is your question on power series?
So I know for previous years for single variable power series, you always wanted to determine the coefficient and a variable and its power. You have to get it in that exact form. Is there an exact form that you get a multivariate power series into?
It's the same thing. It's like they should be written in terms of a multinomial. So like, for example, if you have f of x, y, z, you know, you want the power series centered at, let's say, 1 pi 42, that means you need to write it in terms of, basically you want the power series to be in terms of x minus 1, y minus pi, and z minus 42, right? Powers of these things. Powers and product of these guys. That would be a power series. So like that's, if I was asked to write a power series for a function of 3 variables centered at 1 pi 42, that means I need to put it in terms of x minus 1, you know, y minus pi, z minus 42. So it's the same thing as before. Now if you're asking me like what the meaning of the coefficients is, I'm not really willing to say beyond like order 2 because that's a discussion I've been intentionally avoiding in here. But we do know the formula is up to like order 2, the meaning of the coefficients. Let me just give an example. So if I had f of x, y, z equals to 13 plus 2 times x plus 1 plus, you know, 3 times y plus 4 times z minus 2 plus 1/2 times x plus 1 squared plus 17 times x plus 1 times y, and then plus dot 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 dot, and it's understood that this is it to order 2, then I can read all kinds of information from this, right? Like I can tell you from looking at these three that the gradient of f at the point minus 1, 0, 2 is actually equal to 2, 3, 4. The meaning of this coefficient, right, is going to be 1/2 fxx at the point in consideration here. So from this, I can decipher that the xx derivative at that point is 1. And it just so happens that when I look at the multivariate power expansion, this one, because it's an xy term, it actually ends up, the meaning of this is actually fxy at minus 1, 0, 2 equals to 17. So there's the half doesn't figure into there. So it's simple enough for order 2. There's a half for the double derivatives, and there's not a half for the mixed derivatives. So like, from looking at this, I can tell you other things. For example, like fyy, fzz, fyz, fzx. These are all equal to 0 at the point of consideration. Why? Because there's not those terms there. Is it a max or a min? Like would f of, this right here tells me that f of 0, excuse me, f of minus 1, 0, 2 is equal to 13. Question, max, min? Neither? What would you circle? Neither. Why is that?
Because the gradient is non-zero.
The gradient's non-zero, therefore it's not a critical point, but if it is a critical point, the gradient being 0 is a necessary consequence, necessary condition if the derivatives exist, and they do here, apparently. So, yeah, neither.
plus this plus da, 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 da. We have to actually write out the sum?
I don't think I would actually make you guys write out the sum here. Like I'm content to just work at the level of plus dot dot notation for the most part. Like we haven't needed the sigma notation in this class. I do force the issue in Calc 2, admittedly, a lot. But yeah, I don't think I've really done that in here too much, and I don't. I could think about how to make it an issue. See other questions? Here's a simple one. Example 2. Suppose you're given that f of x comma y is equal to 13 plus 2x squared minus 5xy, all right, plus 7y squared plus dot 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 dot, all right? So then the question is 0, 0 a critical point? If so, what kind? Does that question make sense to you guys? In other words, what, is it a min? Is it a max? Is it a saddle? Right? So how would you do that here? So first of all, it is a critical point. Why? See what's missing here? No x or y terms. That tells me that fx of 0, 0 is equal to fy of 0, 0 by examination. So those are 0. So yeah, the gradient of f at 0, 0 is equal to the 0 vector, so it's critical. And then we can use a second derivative test, right? So what is fxx here? What is fxy? What is fyy? So again, for the double derivative, the meaning the coefficient is it's 1/2 the xx derivative. So I just do 2 times 2, which is 4. For yy, I do 2 times 7, which is 14, I think. And for fxy, again, it's the mixed derivative, so there's no 2, there's no combinatorial factor in this case, and you just get -5 there. Now what's the second derivative test say to look at? It says to look at the Hessian, if you like, the big D. So big D at 0, 0 would be fx 0, 0, fy, y, 0, 0, minus fxy at 0, 0 squared. And that is what? 4 times 14, right? Minus 25. So what do we got here? What's 4 times 14? 56 minus 25. Is that 31? I think it's 31, right? That is what? That is greater than 0. What does that tell us? That tells us the second derivative test applies. And so is it a max or a min? Remember, since the x derivative is positive, that implies that f of 0, 0, which is equal to what? What is f of 0, 0 for this problem? 13. And you guys tell me, min max. Local fill in the blank for me. Nobody? Minimum, right. So it's just like the second derivative test in Calc 1. When the second derivative is positive, it's a local minimum. Second derivative is negative, it's a local maximum. A given, of course, the condition that the big D is greater than 0. If big D is less than 0, it's a saddle. If big D is equal to 0, you have to consult other means. All right? Any questions? All right, let me shift gears here then. Let's talk about the closed set test. And here it is in a nutshell. If D is closed, let me say R. If R is a closed set with boundary R, then a continuous function f, all right, from, let's say, from R to the reals attains, a maximum and minimum, I can't spell, minimum on R. So logically, what does that mean? Number one, max min could be inside the interior of R. Or number two, the max min could be where? On the boundary of R. So what's the test? The test is, if you have a closed set, all right, and you have a continuous function, you want to find out if it's maximized or minimized on that set, you got two places you got to check, right? You got to check inside the set, and you got to check the boundary of the set. You check those two places, and then you just pick winners and losers, and this is how you min-max a function on some closed test. So let me show you an example of this. So I'm going to make this kind of an Uber example, if you will. Well, no, I'll tell you, I'll be concrete here. F of xy, 3x minus y. All right. So that's my quote-unquote objective function. I'm trying to maximize and minimize that. All right. And I'd like to do it on the region R. So let's define this region R by -1, 4. Let's say 1, 1. Oh, that's not very reasonable. That should be like -1, 2 in my picture. I'm sorry. And maybe this is 1, 1. And then I'll be friendly to us. I'll put at least one point on the axes. And then down there, that'll be, let's say, -1, 0. And I'm thinking in particular of the region which is bounded, is inside the triangle. Okay, I'm going to use some color coding here. So I'm going to give the upper leg a red color, and then I'm going to do this blue one right here, like so. All right. And this one like here. So like that. All right, so I'm trying to figure out, and this is my overall my quote-unquote region R. The question is, for that function, where is it maximized and where is it minimized in the region? All right? Does everyone understand the question? So let's do the easy part. Let's check the interior. This is going to be like stupidly easy. What's the gradient of f? Anybody? What's that? 3, -1. That's right. It's not a trap. It really just is that. That is not equal to 0. So what's that tell you? No local min-max inside R, right? So that means there is no place inside the triangle where it could be largest or smallest, right? So whatever max min it has to happen on the edge. Now, what did I tell you guys about how to find the max or minimum of a function on a curve? I emphasized the use of what? Lagrange multipliers. That is absolutely not the right tool for this problem. Because Lagrange multipliers you'd have to treat it 3 separate cases. You'd have to, you got 3 separate lines. This is ill-suited to Lagrange multipliers. There is another way. The other way is much more low-tech, which is that you simply evaluate the function on the boundary and evaluate it as such. So to do that, I have to actually parameterize each one of these cases. So let's do that. 1, 2, case 3. Sorry, my color coding is slipping. But case 1, can you parameterize this? What do you got? R of t is what? It doesn't really matter orientation, whether you go left to right or right to left. It matters not. So which one do you want to take to be the initial point? I'm going to take -1, 2 to be the initial point. And then I'm going to do t times what? 1 minus a minus 2, which is 2. 1 minus 2, which is -1. What'd I do? Oh, yeah. Sorry. Thank you. I'm not trying to, no, in modern geometry, that's the kind of picture you might draw. But in modern geometry, it's about like halfway through the semester before you even talk about distance between points. It's all like axiomatic. 2t. Oh, my bad. That was minus t. 2 minus t, right? All right, I better have you guys double check me on this. Is that right? Okay. So this is my x. This is my y. So if we look at, let's say, g1 of t, which is going to be f of r of t, and I probably should call this an r sub 1 because there's going to be an r2 and r3. What is it actually equal to? I do 3 times -1 plus 2t, right? Minus y, which is that. And let's see here, what's that give us? -3 minus 2 is -5. And we get 6 plus another one, so plus 7t, right? And this is for what? 0 less than or equal to t, less than or equal to 1. Why? Because that's how I built the formula, right? We can parameterize a line segment in this way. Right? If you don't know this yet, you need to fix it. All right, so I'm trying to maximize g sub 1, right, which is nothing more than the function restricted to line segment 1. How should I do that? I've got a function of one variable. We know how to maximize and minimize this on a closed test because we know the closed interval test, right? So like, notice that g1, what is g1? g1 prime is equal to what? 7. And what's g1 prime prime? 0. What does that tell you? Just like f, the max or mins of g1 also have to occur on the endpoints, on the edge. There can't be a place between 0 and 1 where it's maximized. So if I check g1 of 0, and if I check g1 of 1, those are the places where the function restricted to the red leg could be maximized or minimized. So what is of 0? that would be f of minus 1, 2. And this one would be f of 1, 1. What are those equal to? I just got to go plug back in. Minus 3, minus 2, so that's minus 5, right? And f of 1, 1 would be 3 minus 1, which would be 2. Do you guys follow the thought process so far? Let's look at 2. For 2, we've got x equals to, how can we parameterize 2? I'll go from 0 to, I'm going to go from R2 of t, I'll parameterize as, I'll start at the bottom point, and then I'll do 1 minus, so I get 1, up 1, I mean over 1, up 2. So I've got x is equal to t, and y is equal to minus 1 plus 2t. I think that checks for 0 less than or equal to t less than or equal to 1. Do you guys agree? Just double check it. When I put t equals to 0, I'm at the bottom point. What happened to my point? How did it move all the way down there? That's weird. When did I do that? Oh well, anyway. Weird. All right, so does it make sense? T equal to 0 gives me x equal to 0, y equals to minus 1, which is there. T equals to 1 gives me x equals to 1, y equals to minus 1 plus 2, which is there. Okay, check. Now I'm going to calculate G2, which for me is going to be the restriction of f, in other words, f along that line segment, which is 3 times t minus 1 plus 2t, which is what? 3t, my bad. What's 3 minus 2? It's just t, right? And then I've got plus 1, t plus 1. So again, notice that G2 prime is equal to 1, G2 prime prime is equal to 0. Thus, by closed interval test on G2 over the interval 0 to 1, we find G2 of 0, which is equal to f of 0 minus 1, which, by the way, is equal to what? 1. And G2 of 1, which is equal to f of 1, 1. We already calculated that in the previous case. It's equal to 2. These are the max-min with respect to the red segment, case 2 for f. All right, there is yet another case, right? One more case to go and we're done. Case 3. Case 3, what's our parameterization? R3, I don't know, which one do you guys want to start at? The top or the bottom? Doesn't matter. Top. Thank you. I need someone to make a decision. I have trouble making decisions this time in the morning. So minus 1, 2 plus t times, so we go, let's see here, over 1, and we go down 3, I think. So minus 3. Now we can check that. So this tells me x is equal to minus 1 plus t. This tells me that y is equal to 2 minus 3t for 0 less than or equal to t less than or equal to 1. Does that check? Let's check. T equals to 0, I get minus 1, 2, which was here. If I put t equals to 1, I get minus 1 plus 1, which is 0 for x, and 2 minus 3, which is minus 1 for y. Good, it checks. Those parametric formulas for my green line segment do indeed check. Now, up next we calculate G3. g3 of t, which will be f of r3 of t. So we're just restricting the function to the line segment. And that's going to be straight up 3 times minus 1 plus t minus parentheses 2 minus 3t, which is going to give me a minus 5 plus 3t, I think plus 6t, I believe. And again, you notice that g3 prime is equal to 6, whereas g3 prime is equal to 0. That shows me there's no critical points on 0 to 1 is interior. So the min and max of this function of one variable has to occur at 0 or 1 respectively by the closed interval test from Calc 1. So then g3 of 0 is what? It's actually f of what? Minus 1, 2. And g3 of 1 is f of 0 minus 1, I think. We've already calculated both of those in the previous work, right? F of 0 minus 1 was 1. F of minus 1, 2 was minus 5. All right, we have now exhaustively searched for maximums and minimums of this function on both the inside and the edge. So what's the conclusion? We need to look at all the possible contenders here. We've got minus 5, we've got 1, we've got 2, we've got 1, we've got minus 5, we've got 2. Can you summarize what this calculation says? If you're maximizing f of 3x minus y in a triangle, what do you need to do? Like once you work through this, if you had a similar problem, right? Suppose instead of these 3 points, I give you a different 3 points. It's going to work out exactly the same. What is the result? What do you need to check actually? What's all that matters? Yeah.
Value at the vertices.
The value at the vertices, right. So this result, what I'm telling you, is known as linear programming. Like if you've seen it in high school algebra, some high school algebra courses, you'll actually learn that if you're solving a system of constraints, like a system of linear constraints, so you could say y is less than or equal to this line, y is greater than or equal to the blue line, y is greater than or equal to the green line. Find the, find where 3x minus y is maximized or minimized subject to those 3 linear constraints. Well, that kind of problem you can solve just by looking at the vertices. This is known as the method of linear programming. Now, so this is properly speaking part of linear programming. Properly speaking, it's part of what's called operations research, I think. And so they have a way of doing this in more generality, introducing something called slack variables. Slack variables, as I understand them, roughly turn inequalities into equalities with extra variables, something like that. And if any of you guys are like applied mathematicians, you might go take that course. It's a course I've never taken. I just know things a little bit, not that much. So in short, what was the max and min? Maximum was what? Looks like it was 2, right? So the maximum of 2 was attained at the 1, 1 corner, and the minimum of -5 was up here. So this one, max of 2, and right there is where the minimum of -5 was obtained.
Does the 1 does it just doesn't mean anything at all?
The 1?
You have -5, but the only other and 2, but the only other number is a 1. Does it mean anything, or?
That means I miscalculated something, I think. Oh, well, that's just the value of f down here.
Okay.
Yeah. So I think if you were to look at this, you could start understanding it like there's a way to solve this more easily. In terms of like non-calculus, you could think about it like, well, I don't know if it's non-calculus, but if you look at 3x minus y equals to a constant, let's say k, you could think about this as y is equal to k minus 3x, right? Oh, excuse me, 3x minus k, right? So in view of that, Can you guys see why the answer should be what it is? So like this is level K curve, right? So but it's minus. So and the slope is 3, right? So if you're looking at the level K, the level curves of your objective function look like this, right? So the more negative the y-intercept of the level curve, the higher the level. So as you look at level curves here, right, of slope 3, this one would have a more negative y-intercept than that one. And this is the y-intercept. So anyway, you could, but I don't know. I think that it's much more interesting to analyze it in the way we did. Because the way I've just showed you how to analyze this thing, if instead of having f of x equals 3x minus y, what if instead of that you had like 3x squared minus y squared? See, we can still solve that problem with calculus 3. What happens if I change that to 3x squared minus y squared? I mean, I'm not going to work it out, but like just hypothetically, what would happen here if I change this and I put a square up here and a square up here? Can you guys kind of qualitatively tell me what's going to happen to the calculation? First of all, the gradient is going to have what? The gradient's going to, this is kind of quantitative, but forgive me. So the gradient's going to be 6x comma minus 2y, right? All of a sudden, the origin is a critical point, right? And the origin is inside this, so the origin's relevant. So we'd have to check the origin, for one thing. It's 0 there, but whatever. Then, as you were to look at this function restricted to the legs, right? You're not going to just be able to sweep the leg to the endpoints, right? Like you're going to have to like deal with it, because when you square this or square that, you're going to get a t squared, which means the second derivative isn't just going to be 0, and the first derivative is going to be linear in t. In fact, there may well be a critical point interior to each leg. So you're probably going to have to check like a maximum or a minimum both on the endpoints and possibly the interior of the leg. So those calculations are going to get more interesting. So anyway, there's going to be much more to check for that function than the linear function. Yeah.
What if R was a circle?
Ah, great question. Let's look at one of those. So as you have just experienced, it takes a long time to actually work one of these out by hand, which is why this projector is a blessing. Because, well, you guys could, of course, watch me work out max-min problems for weeks on end, and it would be very interesting. I know some of you are itching, literally itching, to get to, what's it called? Oh, yes, integration. So I do intend to start integration tomorrow. I've explained to you the method, right? Now you got to put it into practice, is what it boils down to. Now here's one. This is almost what you asked for, Violet. Almost. This example's on a half circle. Well, a half disk. All right, so like x squared plus y squared less than or equal to 4, y greater or equal to 0. And this function is not linear, right? So it's going to have interesting gradient. In fact, the gradient of this, x to the 4th plus y to the 4th minus that, gives me this. If I set that equal to 0, I either need y equals to x cubed or I need x equal to y cubed, which gives me x to the 9th equals to x. Ever solved x to the 9th equals to x? It's not bad. So you just factor out an x. You got x to the 8th minus 1, but that's x to the 4th times x to the, this. That's got no solutions because you can't, there's no real solution to that guy. It has 4 complex solutions. They're kind of pretty. But anyway, so you've got this and that which have no real solutions, and the real solutions to this are in fact 0, minus 1 and 1. So that gives me, when I go back to my context here, I get y equals to either 0, 1, or minus 1. I'm not sure I believe that. Oh, I'm a dummy. Critical points, right? So it's not these equations I'm going back to, it's these equations I'm going back to. If x equals to 0, y equals to 0. If x equals to 1, y equals to 1. If x equals to minus 1, y equals to minus 1. That's why I get this, this, and that. Okay, great. So those are my 3 critical points. And what is h? Maybe it's good to draw a picture of it. H is this half circle kind of deal, right? This is radius 2, right? So in that 0, 0 is down here. And what was the other one? 1, 1, well, that's up here somewhere. But minus 1, see, minus 1, that's out of the running. So like that critical point, it need not concern us because it's outside the domain of consideration here, right? See that? Right, it's down here, so it doesn't count. So we only need to look at the origin and 1, 1. And in some sense, I don't know, I'm kind of, you should just, it doesn't really matter if it's, you don't really need to check these. This is just an idle curiosity. Like, technically speaking, does it matter if it's a saddle or a local max or min? Not really in this context, because you're just going to find all of the possible critical points for your function on the half disk, and you're going to see which one's the winner, which one's the loser. But just for extra practice, I'm checking the second derivative test here. And I find out that 0 is a saddle, and that 1, 1 is actually a local min. All right. Now, I need to look at the boundary. The boundary here has got 2 pieces, right? It's a circle and it's a line segment. The double scrolling. It got me again. Stupid double scrolling. I hate you, double scrolling. All right, so here they are. The diameter, in other words, the line segment, I just I put y equals to 0 and x equal to x for minus 2 less than x less than 2. And g of x is f of x 0. That's the value of the function on the line segment. On the diameter, I get x to the 4th plus 1. And then I can study that by the closed interval test. So g prime is this. In fact, we are x equal to 0 is the only critical number there. And lo and behold, these are the values to think about. 17, 1, and 17 on the endpoints. All right, so we should keep those in mind. Then the curved part of the circle, well then what we can do, so here's the thing. For the curved part of the circle, you could either use Lagrange multipliers with like your attention focused just on the part, which is the upper half circle, right? But I find sometimes it's better just to use a parameterization for the circle and like plug it in. So here we have x equals to 2 cosine t, y equals to 2 sine t. That's a parameterization for the circle, right? If I limit 0 to pi, that's just the upper half circle, right? And so then I plug in those into the formula, and that gives me this beautiful formula. Sine to the 4th, cosine to the 4th minus sine cosine. And I differentiate that, like so. And then I set the derivative equal to 0 to look for critical points in t. And that produces for me actually that the tangent of t should either, so look at this. Do you see this, the product here? So either this is 0, that is 0, or this is 0. Those respectively give me tangent t is 1, minus 1, and this gives me sine of 2t is minus 1/2. So anyway, so I get either pi over 4 or 3 pi over 4, or 2t is 7 pi over 6. And then let's see here. So I get 4 different interesting values of t on the half circle. This is a pretty nefarious problem, right? There's a lot going on in this example. As a homework problem, this would take me at least an hour. All right. So these are the points. If I plug in those 4 values, critical values for t, I get these 4 points, which, you know, I think really for this kind of problem, you definitely want to go decimal because otherwise it's really hard to like compare things, right? And you are trying to pick a min and a max, so it's helpful to have the decimal approximations for the sake of comparison, if nothing else. And then I plug these into the function, and I get this, that, and that after I take x to the 4th plus y to the 4th. What was it? I forget the formula, but I know it's got an x to the fourth and a y to the fourth in it. So I do all that. And then which one's biggest and which one's smallest, I don't know. I got a 19 there. That looks like it could be a contender. We had a 17 before, right? But 19 is bigger than 17. All right, so what happens here? Of the 9 possible extremal points, good grief, this example, the minimum value is -1, which is attained at 1, 1. So the local one actually was where the minimum was. And the maximum is approximately 19, which is attained at these 2 points. And here's a graph of what just went on. So this is basically the image. So the domain, if you will, is just the half disk. And the function f, if you set z equals to f of x, y, this is what the graph looks like. And so that's why the -1, 1, the 1, 1 was like the minimum. And somewhere up here is where we hit the 19. So, yeah.
Did you already evaluate along the possibilities also?
I did. That was case 1 here. I know it's been a while, but like this was the diameter. That was the case 1. But yeah, you got to check the whole boundary, and it's annoying. If the boundary is made up of different things like lines and circles, you probably need to evaluate them separately. This example I worked out carefully in class for you with different numbers, but the story remains the same. If you've got a linear objective function and you're maximize, minimize on a triangle, you just check the endpoints is what it turns out to. Now, if I give this problem on a test, I don't want you to just tell me we just check the endpoints. I want you to work it out with Calculus 3, okay? This is not a high school algebra class, so I don't expect you to just memorize the answer, you know? You should recognize that this is a pretty easy problem. It's just got a lot of writing, right? In contrast, the example I just went through on the half circle is not an easy problem, and it actually required like pretty nefarious algebra, I would say. Now, this one might actually be the answer to your question, Violet. So here I have f of x, y equals 2x cubed plus y to the fourth. I'm supposed to find the absolute extrema of f on the unit disk. So that's just straight unit disk. As you can see, Math 200 people take off 50% of my credit. I missed a curly bracket right there. My bad. So I calculate the gradient. I get the origin's a critical point, so I got to check the origin. Right? Wonderful. And then, so let's see here. On the boundary, whoa? Oh, okay. Oh, here's an interesting thing. So I resisted the urge on this one to just parameterize the boundary. Instead of just parameterizing the boundary, what did I do? I took advantage of the equation of the boundary. I simplified the function with respect to that equation. That makes it easier, actually, here. See, because y squared is 1 minus x squared on the boundary. And my formula, I have a y to the fourth, right? So to convert this to just a function of x, all I got to do is look at that as y squared squared. And I straight up get this as the restriction of f to the boundary in terms of x. X turns out is a nice parameter for the whole boundary in that regard. And then I can just do calculus 1 on it. I set the derivative equal to 0. I find my critical numbers. I plug in them. And I get these are my possible min-maxes. And then we pick winners and losers. This is the closed set test. So here's a picture of it. So it turns out that it's like minimized down here. It's maximized up here. And there's some kind of like funky saddle points in the middle. But all right, so listen, you guys can ask me more questions about max and mins in like future classes. That's totally fine. But I'm going to move on to integration tomorrow. So, yep.
Is our quiz on the stuff we did today?
Our quiz is on everything we've done optimization-wise. Yeah. When is the quiz supposed to happen? Tomorrow? Okay.